Hello AP Chem students and welcome to topic 9.2, absolute entropy and entropy change. The learning objective for today is 9.2.a, calculate the entropy change for a chemical or physical process based on the absolute entropies, standard molar entropies, of the species involved in the process. So you might remember from topic 9.1 that we did talk about the concept of entropy, and we looked at comparing entropy for species and thinking about if the entropy is increasing or decreasing or greater than or less than. In this topic, we're actually going to look at quantitatively calculating the entropy. And I really quite like this graphic. I think this is fun. So entropy is the basis for the second law of thermodynamics, which says that the state of entropy of the entire universe as an isolated system will always increase over time. And this is a pretty fundamental law for us, and it is what determines a lot of the laws that we act upon in other areas. For example, it is how we know that the universe is expanding, because the expansion of the universe is based on the second law of thermodynamics. It's also, by the way, why your room is hard to keep clean, because you're always moving towards a state of increased entropy. So to determine if the entropy in a system is increasing or decreasing, you can calculate the change in entropy, which is delta S. Just like with enthalpy, we cannot measure directly the entropy of a substance. However, the third law of thermodynamics states that the entropy of a pure, perfect crystal can be taken to be 0 at 0 Kelvin. And so we can extrapolate. If we compare species to that value, then they are able to determine what the relative entropy of any substance is. So we also know that entropy depends on temperature, and so they can calculate standard entropy values. You will be given those values, and you just need to know how to calculate with them. First of all, an important thing to note is that elements in standard states do not have a delta S standard equal to 0. So that is different than enthalpy. So I wanted to show you some values here. So you can see this, that the elements do not have standard entropy values of 0. Here's hydrogen in its elemental form is 130.6. Nitrogen in its elemental form is 191.5. You can see that as our molecules get, as our atoms get larger, the entropy value increases, okay? And that's because of that kind of idea of dispersion. You can think of it in a lot of the same way that we talked about kind of the electron cloud and how it can disperse a bit more as you increase the number of electrons. This is different, but it is kind of the same concept. A standard entropy value is the entropy of 1 mole of substance in its standard state. So the standard state is the state in which an element exists at 25 degrees Celsius and 1 atm. In general, the more atoms in a molecule, the greater the entropy of the substance. And this is actually, I think, a little more straightforward to understand. So if we look at the liquids here, you can see that we've got water with 3 atoms, and that's got a standard entropy of 69.9. Methanol has got 4, 5, 6 atoms, and that's 126.8. And then here we got C6H6, and that's got 12 atoms, and that's 172.8. And so the reason I think this is actually a little more intuitive is because if you think about the microstates and the fact that we're looking at the dispersion of energy and matter, energy has different locations it can go to here, all right? You have a greater number of bonds that are present in the molecule, and so that provides a higher number of microstates and therefore a greater entropy because your dispersion is increasing. We can look at another series here. You've got methane, ethane, and propane. And you can clearly see based on the values that as we increase the number of carbons and the associated hydrogens, our entropy increases. So delta S values, will either be provided to you in the question or in the form of a table as you see here. So using this equation, so we've seen this equation before, we use the same equation with enthalpy. So you can calculate the change in enthalpy for a reaction by doing your sum of your, I said enthalpy again, entropy. You can do the change in entropy of a reaction by doing the sum of the entropy of your products minus the sum of the entropy of your reactants. And just like we did with enthalpy, you'll be using coefficients to multiply as well. So we're going to look at that right now. So here's practice 2. So calculate the delta S standard for the decomposition of dinitrogen pentoxide shown in the reaction below, given the entropy values for the species in the table at the right. So here's your reaction, here's your species. If you want to try this on your own first, please go ahead and pause the video now. I'm about to go through the answer. Okay, so we're going to use this equation, which by the way, you might know is off the equation sheet. You can see that based on the formatting. So this will be in the drop down on the AP exam that is in the thermochemistry and electrochemistry section. So we're going to have our products minus our reactants. So we've got 4NO2, and that's in gaseous form, which we see over here. And then we've got 1O2 in gaseous form. Now, I did show you both the gas and the liquid to drive home again this idea that gases have much more entropy than liquids. So you can see here, if we compare O2 liquid to O2 gas, the O2 gas has got almost twice as much entropy as the liquid. So that is, a lot greater. And so then you subtract by 2, which is your coefficient of your reactants, times the N2O5, which we see over there. So now we can plug in the values, and then you can let your calculator do the heavy hitting, and you get a value of 455.4. So then the question is, does this make sense? And we want to do a little quick check of our work. So we started with 2 moles of gas in our reactants, and we ended with 5 moles of gas in our products, which means that we are going towards a greater number of moles of gas, which means that we would expect our entropy to increase and be a positive value, which is what we saw. And so this answer does make sense. So what should you be able to do with this? You should be able to calculate the entropy of a system given the entropies of component species using the sum equation that we've seen here. Now, as a reminder, what we did in topic 9.1 is we did some qualitative comparisons of entropy. Is entropy increasing or decreasing? Which species has greater entropy? So you should also be able to do that. So sometimes you will have to be able to compare entropy without values, in which case you would look more at the qualities of the system, but then you should also be able to calculate a quantitative value for entropy if you're given the values in the problem. And that's it for this topic, and I'll see you soon for topic 9.3.